In this video, we are going to work on the titration of a monoprotic weak acid with a strong base. A mass of 0.51 grams of potassium hydrogen phthalate, or KHP for short, is placed into a 50 milliliter volumetric flask and diluted with water. It has a molecular weight of 204.22 grams per mole and a Ka of 3.90 times 10 to the negative 6. This acidic solution is titrated with 0.1 molar sodium hydroxide. What is the pH for the following volumes of titrant added? Now, we know KHP is an acid, not just because I tell you it's acidic, but if you're titrating with sodium hydroxide, you should all know sodium hydroxide is a strong base. Therefore, that means that the other species is an acid. But how do we know it's a weak acid? Well, it has a Ka. Anything that has a small Ka value is going to be a weak acid. So we're going to essentially perform a titration. And so what we've got is we are going to slowly add volume of our titrant, that being sodium hydroxide, to our solution, and we're going to see the pH change. Now, it's an acid, so the pH is going to start low, and then as we add sodium hydroxide, we're going to slowly increase the pH until it kind of levels off. And so that is what's called our titration curve. And so at each point, we're going to be looking at a different volume of our titrant added, and we're going to figure out what is the pH at every single one of these points. So this first point here is point A, B, C, and this last point is point D. And so let's work each one slowly and systematically and see what we can learn about titrations in the meantime. So to begin with, for letter A, we haven't added any titrant at this moment because it's 0.00 milliliters of sodium hydroxide. So no titrant has been added. So what do we know? That means that all that's going to determine the pH is our potassium hydrogen phthalate and the water. Now we know the Ka of our solution, and we also know our molecular weight. We're going to need those two pieces to go forward. Now, I could write out KHP, but I'm going to remind myself that it is a weak acid. The symbol for a weak acid is Ha. Any weak acid is going to dissociate into a proton and its conjugate base, which we see here. Do note the two arrows are going to designate that's an equilibrium reaction. So what happens is we essentially are setting up an ICE table. I for initial, C for change, and E for equilibrium. And in this box, or this table, if you will, we're going to put what is the initial concentration of each species, what's the change, and what's the equilibrium. But we're going to do that as concentration. So that's my first step. I know I place 0.51 grams of KHP into a 50 milliliter volumetric flask. That's the same thing as 0.0500 liters. Now I need to convert my grams to moles. So I do 204.22 grams per 1 mole of KHP. And this will allow me to convert this to molarity. And so I get a formal concentration of 0.050 molar. And so I call that formal concentration. Formal concentration is just another way of saying what concentration were you given in the problem. All right, so that's my formal concentration. I therefore can go over to my table and say my concentration initially of my weak acid HA is 0.050 molar. I didn't start out with any hydrogen ions or any conjugate acid, so those are both 0. My change, this one's going to decrease while these increase because they can't decrease because they started out with nothing. So they're going to go down while these two are going up. And then my equilibrium is 0.050 minus x, and these are both x. So if I plug these into my equilibrium expression, we have Ka equals my hydrogen ion times my conjugate acid over my acid. Sorry, did I say conjugate acid? I meant my conjugate base. And so now I just plug in my values here. And so my Ka was given in the problem 3.90 times 10 to the negative 6. We can see that right here. Equals, my H is an X, my A is an X, so that leaves me with X squared on top, over this entity here, which is my HA concentration, which is 0.050 minus X. And so this is where we get the expression And so this is where we get the expression for any weak acid problem. It can reduce down to Ka equals x squared over F minus x, where F is just simply that formal concentration we found earlier. It's that same format, but it comes from that ice table that we originated with over here. All right, so now we just have to solve. So since my formal concentration here, 0.050, is at least 100 times my Ka, which is here, since it's 100 times greater than that, we can pretend this x right here is non-existent. So it goes to 0, which means we can simplify this down to 3.90 times 10 to the negative 6 equals x squared over 0.050, which essentially just means we don't have to do the quadratic formula. So now I multiply 3.9 times 10 to the negative 6 by 0.050, and I end up with 1.95 times 10 to the negative 7, and that equals x squared. Take the square root of both sides, and you end up with x equal to 4.416 times 10 to the negative 4. Now, what do we do with that? What were we trying to accomplish? We are trying to accomplish and determine the pH at this point in time. What does X stand for? X here stands for my hydrogen ion concentration. So that is H+. So in order to find pH, we know pH equals negative log of my hydrogen ion concentration. And so that's equal to negative log of 4.416 times 10 to the negative 4. So we end up with a pH of 3.35. Let's check our sig figs here. So we had 2 sig figs in our formal concentration, and that's going to be our lowest number of sig figs, which means really this value here has 2 sig figs. And the rule for taking the sig figs from a log is however many sig figs are in the number you're taking the log of is going to tell you how many decimal places you need to report. Okay, so 2 sig figs means we have 2 decimals. All right, let's go forward. So let's go ahead and mark this on my pH here. So what is my pH at point A? It's 3.35. I like to draw my chart and mark on it because it helps me realize if I ever made any errors. I know my pH needs to steadily increase as I add my base, and if it does not do that, then I made an error somewhere, either mathematically or logically. All right, let's do the next point. Point B, what happens after I've added 5 milliliters of sodium hydroxide? What is the pH? All right, for this problem, I like to remind myself of what I know before I get started. So I know I have 5 milliliters of sodium hydroxide. I have 50 milliliters total volume to start out with, and then I have, that's my molarity of my HA, and then 0.0025 moles of that. And so whenever I make my ice table, it's not really an ice table now, it's more of a reaction table because we are reacting our HA with our sodium hydroxide. Now, sodium is just a spectator. Hydroxide's the part that's going to truly react with our HA, with our acid. Now, we are going to put a single arrow because the single arrow indicates this reaction only goes forward. Anytime you have a strong base, it's going to force our weak acid to give up its proton and react. And so anytime you have a strong acid or a strong base as a reactant, you're going to have a single forward arrow. So how does this react? Well, when hydroxide pulls off a hydrogen, it's going to form water, and you're going to be left with your conjugate base. Notice both mass and charge are conserved in this equation. All right, now I'm going to plug in moles because that's easier for me to see stoichiometrically. Meaning, initially, I'm going to start out with 0.025 moles of my HA. And then for my hydroxide, I need to figure out how many moles of hydroxide I have. Well, I know my molarity, which was 0.100 molar. And so if I take that times my volume, because remember, molarity is just moles per liter, so I need to multiply in order to figure out how many moles I have. So times 0.0005, and that's in liters because I converted from milliliters to liters. And that means that I end up with 0.0005 moles of hydroxide, or 5 times 10 to the negative 4. I started out with no water and no conjugate, and then as these react, these are both going to reduce, and I'm going to increase for my product. Now, how much is it going to reduce by and how much is it going to gain? Well, look at your 2 moles. Remember the concept of limiting reagent? I can only react as much as I have. I cannot make up other species to react. So which one am I going to run out of? Hydroxide or my weak acid? Hydroxide. And so I'm going to lose 0.0005 from both sides, from both my HA and my hydroxide. And at the same time, I'm going to gain both my water and my conjugate in the same amount because they're all stoichiometrically equal to each other. And so now I complete my table here, and so I'm going to end up with 0.002 moles of HA, 0 of my hydroxide, and 0.0005 of my water, and 0.0005 of my weak base. Now, water is not going to affect my, my pH as much as a weak acid or a weak base will. And so we can pretty well just ignore my water. But we have both the presence of a weak base and a weak acid. And so what that's going to be is a buffer. A buffer is composed of both a weak acid and a weak base. And it's composed of these 2 entities in order to resist the change in pH. If we come back to our graph, we can see this region right here is a region at which the pH does not change appreciably. And so this region is called my buffer region. So if it's a buffer, we have something called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation states that pH is equal to the pKa plus the log of my base over my acid. And I'm going to use my little conjugate base formula and an HA formula. So we have the base on top and the acid on bottom. And notice we did have hydroxide, but this is all in reference to my equilibrium concentrations. Even though we had base as a strong base form, that has all gone away. We have none left, 0. Okay, and so we're referring to these entities that we see right here and right here. That is my concentrations of my acid and of my base. Actually, they're not my concentrations, right? Because concentrations are equal to moles per liter. But what's really nice about this format here is if you have moles per liter on top and you're dividing by moles per liter and they're in the same container, which these are, we have a total here of 55 milliliters because if we add these together we get 55. But what's cool is my liters are going to cancel out, so I can essentially just place my moles into this equation. And so I could convert both of these moles into molarity before sticking them into my Henderson-Hasselbalch equation, but since they're in the same container, they're going to cancel out and I can ignore their effect. Okay, let us plug our values into this equation. So pH equals pKa. We do not have the pKa of our substance, but we have its Ka. So the little p here, all that stands for is negative log. And so if we take the negative log of our Ka value, which our Ka value, remember, was 3.90 times 10 to the minus 6, and now we can add the log of our 2 molar amounts. And so our conjugate base, we have 0.0005 moles, and we have 0.002 moles of our weak acid. So this gives us a pH equal to, I'm going to solve for this one first, 5.408. plus the log of 0.25, which is equal to negative 0.60206. And then if we add that to our 5.408, we end up with a pH equal to 4.81. And that's my pH for point B. So I'm going to come back up here to my curve, and I'm going to fill that in here on my graph. 4.81. And so we've solved for A and we've solved for B. Let's solve for C now. Now C, I just simply asked at the equivalence volume. Well, this equivalence volume here, the point on the inflection point on your curve, is called your equivalence point. What that means is your moles of your acid equals your moles of your base. And so that's pretty important. You can use that to figure out how much volume of sodium hydroxide you're going to need to add in order to reach the equivalence point. Now, in a well-done experiment, your equivalence point is going to happen at the same point as a color change if you're doing a colorimetric titration. And so the color change is simply used to indicate that your moles of your acid equals moles of your base. And if the experiment's designed right, the color change happens at this exact same moment. So let's figure out what that is then. So what is my equivalence volume? How can I use this idea that my moles of my acid equals my moles of my base to determine how much volume of sodium hydroxide I would need in order to achieve an equivalence point? So I know that I started out with 0.0025 moles of HA. And at this moment, that equals my moles of my sodium hydroxide. And so what I can do is I can use the molarity equation. Molarity equals moles per liter in order to figure out what is my volume at my equivalence point. So I know my molarity is 0.10 molar, and that equals 0.0025 moles over X liters. X equals 0.25 liters, which is 25 milliliters at my equivalence volume. So now I can use this information in order to figure out what is my pH at this given moment in time. Before we go further, I'd like to note right here that what this equivalence volume is, 25.00 milliliters. Does that make sense? Yes, if we are assuming that at point C, we are going to increase in volume and increase in our pH. And so 25 milliliters is bigger than before in our buffer region. We would expect our equivalence point to have had more base added than at the buffer region. So next, let's start reacting our species together. So we have HA, and we are adding hydroxide to it to form our water, which we don't really care about, plus our base. We're going to start out with 0.0025 moles of our weak acid, and we're also starting out with 0.0025 moles of our strong base. We're starting out with no water, no conjugate. So we got initial change equilibrium for this reaction. These two are both going to decrease. They're going to decrease by 0.025. And that's because both of them essentially are the limiting reagent, or really you can think about it as neither of them are the limiting reagent. They're both going to disappear in the reaction. So that leaves us with none of our weak acid, none of our weak base, some water, which we don't care about, and a conjugate base. And so all we really have at this moment in time is our conjugate base. At this moment, we have a weak base and water. So notice our weak base and our water. That's what we have remaining in our solution. So what type of problem is this? This is a weak base problem. So if we look back at part A, this was a weak acid problem. And so a weak base problem is very similar to this weak acid problem that you see here, where instead of this reaction happening in this direction, it's going to happen in reverse, where your A minus reacts with water to produce, notice the equilibrium arrows here, HA plus OH minus. And so notice that's kind of the definition of a conjugate base, is it's going to produce hydroxide. And so that's our reaction here, which means your KB, which is what's going to describe the relationship between this equilibrium expression, is HA times hydroxide over your A minus. And so if you set up the ice table and made it all work out, you're going to find that KB once again equals x squared over F minus x, except for one big difference. Your X is your hydroxide, which means your F is the same as your concentration of your conjugate, but your X is your hydroxide ion concentration. And so those are your big, huge take-home messages for how you would do a weak base problem. So I'll kind of fast forward a little bit through it. We could write out the whole ice table if we wanted, and might as well. Let's go ahead and do that. So we have A- reacting with water to produce your conjugate acid and hydroxide. And so if we started out with 0.0025 moles here of our conjugate, and we have our ice table, we're going to start out with no weak acid and no hydroxide because, none was left behind before. And then we're going to subtract X, add X, and add X. And so this is where I was talking about how X is now your hydroxide ion concentration. And your formal concentration is related to your number of moles of your A-. But this is in moles, and this is minus X. So we need to turn this into a concentration. How do we do that? How do we get that into molarity? Well, could we just divide it by our 25 milliliters? No, because it is also interacting with the 50 milliliters that we started with initially. And so because of that, we need to make sure that we've got total concentration here, not just, the concentration that I added. It's total because my conjugate is not just in my solution of base, it's in my solution of initial weak acid plus the base that I added. And so here I've added a total of 0.075 liters. And so now that's my formal concentration. So I end up with my Kb equals x squared over F minus x, where your F here is 0.0333 molar. Remember, your X is your concentration of hydroxide. So then, how do I find Kb? Kw equals Ka times Kb. Therefore, Kb equals Kw divided by Ka. We know the Kw of water is 1.0 times 10 to the negative 14, and we know our Ka, which is 3.90 times 10 to the negative 6. That gives us a Kb equal to 2.56 times 10 to the negative 9. Notice here how my exponents add up to be approximately my 14. That's what it should be. 9 plus 6 gives me 14. And so sometimes they'll add up to 15, right around 15 or 14, but it's generally ballpark. That tells you if you did the math right. And so negative 9, negative 6, that gives you negative 14. So that adds up correctly. So now we are going to sub in that value here into our equation, and notice this formal concentration is much, much, much greater than our Kb, which means we can approximate that our X goes to 0. So to finish out this step, we have 2.56 times 10 to the negative 9 equals x squared over 0.0333 molar. So we solve for x, and x equals 9.24 times 10 to the negative 6 molar. And remember, that's not our hydrogen ion concentration, that's not our pH, that is equal to our hydroxide ion concentration, which means we can find the pOH by taking the negative log of 9.24 times 10 to the negative 6 to give us a pOH equal to 5.03 and a pH, which was just found by taking 14 minus 5.03 in order to give us 8.97 as our pH here. Let's go back up to our graph at the top, and let's place 8.97 on our graph. Notice 8.97 is above 4.81, which is what we would expect. But the important thing here, remember, is what we had figured out before is at equivalence point, the moles of our acid equals the moles of our base. This is very important. All right, now let's do the last one. Part D. 35 milliliters of sodium hydroxide have been added. With 35 milliliters of sodium hydroxide added, the big question is, what's my molarity? And what also is my moles? And so I can take my molarity, which is 0.100 molar, times my volume, but my volume needs to be in liters, 0.035 liters. And that's going to give me a number of moles of my sodium hydroxide. And so I have 0.0035 moles of sodium hydroxide. And now I can write my ice table and react my hydroxides with my weak acid in order to produce my water and my conjugate base. But remember, I still have the same number of moles that I started out with. But I've now added in 0.0035 moles of my base, and those two are going to react with each other. I start out with no conjugate. These two are reacting. My change is going to be my limiting reagent, which in this case is my HA. So we're taking away 0.0025 from that. If I chose wrong and I subtracted out 0.0035, I would have ended up with a negative number here for HA, and I didn't. And so I can assume that I guessed correctly because my HA is going to 0, which is what I want to happen. Take that same value away from hydroxide and add it to my conjugate. That gives me 0.0025 for my conjugate, 0.0010 moles for my base. Now what do I do with this? I often see people immediately take this value and plug it in to POH equals negative log of 0.010001 moles. But why that's wrong, absolutely wrong, is it needs to be concentration, not just moles. And so in order to figure out our concentration of our hydroxide, it needs to be our moles, which we have 0.0010 moles, over my total volume. Once again, that's not 35 milliliters. It's 35 milliliters plus 50 milliliters initially. That's important. So hydroxide ions equals 0.0010 moles over 35 plus 50 gives me 85 milliliters. Turn that into liters is 0.85 liters. So my final concentration here of sodium hydroxide is 0.01176 molar. I can now take this and plug in negative log of this value to give me my POH equal to 1.929, which means my pH equals 12.07. I can go back up to my graph at the beginning and plug that value here into the graph and make sure I didn't mess up. Please do this because it will show you when things go wrong. I can see that my pH is steadily increasing with my values as I add in my volume of sodium hydroxide. And with that, you have just completed a complete titration of a monoprotic weak acid with a strong base.